Hello everyone. I would like to welcome to Leonard Nilsson's presentation about induced spatial development. Just for your information, this session will be recorded, but your names will not be visible if you don't ask questions. It will be possible to ask questions after. You can write them in the chat field, and we can read them out loud if you don't want to ask them yourselves. But please, Leonard, you can begin your presentation.
Thank you very much for the introduction. As you said, the title is Induced Spatial Development. And I would like to stress that word induced, because spatial development, I assume you know what that is. We use land and we build, and our urban areas grow. But the word induced is the most central, because that is what our research is about. So now, a more in-depth perspective on induced. We have got a lot of questions on our presentation earlier, so I would like to address those ones more in depth, so that everyone can hear it. And of course, it would be fun with more questions. I'm happy to answer those ones as well. But I felt that during earlier presentation there has been not so much time to address them in depth. So, and following that, I would like to explore our thoughts, our problems, and I would like to and of course our model, and I would like to explain our theories and our hypothesis, because all those are related to this word induced. So, contents, a little short intro, the starting point, retrospect into what earlier scientists has done, and earlier models and theories in this field, the reasoning, why do we do this research? And then I will divide it in 3 parts: background of our model, and then positioning our model in relation to other models, because there are other ways to model this spatial development, and have a little look at the results. How can we interpret the results, and what are the next steps for my research? So, what problems does this research address? Because you always have to start research with a research question. You're trying to answer a question, and you're trying to address problems, trying to make the world work a little bit better and to understand it better. So, urban growth, it doesn't always occur where we want it to occur. To build a sustainable and attractive city. We want, as planners, we would like to make good plans that work in the long term. But urban growth runs a little bit on its own, because the planning process becomes sometimes driven by market forces. That someone wants to establish offices, workplaces, industries, shopping malls, residential areas. And this planning is not always driven by the public policies. And this becomes in some way a democratic problem, that our democratically decided plans doesn't always work as we want. And also the regional development, which I understand is very important in Norway. We are discussing it in Sweden as well, but we haven't come as far as you have. in trying to make the whole country live and prosper. So the activity does not occur where we want it to be, where the infrastructure has capacity, where it's suitable from a land use perspective. In Sweden, we have, for example, a lot of shopping malls that are built on very fertile soil. And when you build on that, you destroy it, you cannot use it in the future for growing crops. And also sometimes you build very dense in the city and you got a lot of problems with congestion because you don't have enough capacity on the infrastructure. Whereas you have other areas where the infrastructure has a lot of capacity, but it's not used. And that's a waste of money. So we would like to be able to control or understand and control this planning process a little bit better. So, and a little bit broader perspective, why is this research important for the E39 project? Because a lot of the research in the E39 project is focused on the roads themselves in the construction, and that is, of course, very important. But I think it's also important to look at the consequences for the built environment, for the urban development, and for the regional development. How will that develop following the E39 project? So we would like to address how does infrastructure changes induce or change the urban growth and the urban activity and the regional development. So, and when we understand that, we can handle the spatial development that this kind of infrastructure will induce. So we can make sure that the growth of buildings take place where it's suitable and in a sustainable way, of course. So basically, we want to understand what we do, and we want to get good return on our investments. So a little bit look at the historical development in this science field. We have these traditional models von Thünen, very old. And that is a quite simple monocentric model, it's called, where you have the central city in the middle, and then when it's a bit cheaper land, then you have intensive farming, and then forestry and etc. And the farthest away from the city, you have the least intensive land use. And you can look at this in this way, that the commerce is willing to pay a lot in rent to be in the city center. The industry is not willing to pay so much, and the residential, the inhabitants are even less willing to pay for a central location. So following that demand and that demand curve and that willingness to spend, we get this result, these concentric zones. We have the CBD, the central business district, in the middle. And then you have the residential on the outskirts, where it's cheaper. So this traditional model, well, it's basically a good way to start understand urban development. But it's problematic in the way that you have to define the city center first, and that this is also just simple concentric circles. In reality, our cities doesn't look that way. They are kind of grids or bent and sprawling in certain ways. So we have to understand that in a better way. So that led to development of gravitational models, where you look at the accessibility to attractions. two workplaces, two shops, for example. And then the next step is more modern models, where you say that everything affects everything, that you don't have to point out which where the city center is and what you want access to. You're looking to kind of a more general model where everything wants access with everything. So now we're going to have a look at our model and a little bit the background, the justification for the model. So we start by looking at the cumulative distribution of activity. And here we use land value as proxy for activity. Where there is a very large activity, people are more willing to pay. So the activity that reflects in land values in a quite good way. I'll come back later to other ways of representing activity. Because there are other ways, but well, every way has its benefits and drawbacks. So, but if we start to look, we look at Sweden this time because Alexander's project has spent tens of thousands of kronor to get this kind of data, so we would like to make use of it a little bit. So you can see these small red areas, that is 25% of the total land value. And now a little bit more areas, there is 50% of the total land value in these small red areas. And here you got the 75% of the total land values are concentrated to these small areas. So 2% of the built area holds 50% of the total land value. That's a very uneven distribution. So we would like to understand that process that generates this enormous concentration of land value. So what makes these 2% so special? Well, maybe you can say that they have a good location, and sometimes that is true. You can see along the west coast there is a lot of attractive locations. But then when you look at cities, what's so special about those areas? Well, there is nothing special regarding the natural geographic constraints, I would say. I mean, in Sweden and Norway, we have forests, we have mountains, we have rivers, lakes, and farmland. So when cities are built on these kind of lands, so there must be something else that makes these 2% land so special. And that process that makes them so special, that is generating, as I said, a very uneven or heavy tail distribution. And it must be some kind of multiplicative growth. Multiplicative growth may be best understood by the rich get richer. When you have a lot of money, you can invest and you get a good interest rate and good return, and then you become richer. Because I assume you know that the wealth distribution in the world is very uneven. Few percent of the people holds the majority of the wealth. So that is kind of the same distribution. A lot of economic activity seems to be distributed in this way. But there's a few percent containing a lot of the value. You have, I assume, always also heard about the 80-20 rule, that 20% contains 80% of the functionality or so. The Pareto distribution. So if we look at the urban growth, as I said, we can have these local conditions, as you see on the left side, proximity to water, if the land is easily exploitable, etc. And as I said, those are not really sufficient. So we're looking at the accessibility of the places. And that's a weighted sum of time to reach other places. And then we look at the accessibility to activities, to, as I said, workplaces, shopping malls, other people. That is some kind of attraction. And that attraction generates activity. As I said, in trade, dwelling, etc. And this increase in activity that creates a demand for new buildings, for taking new land and transform it to something more useful. So, but as I said, the local conditions aren't enough to understand this accessibility, this attraction, and this activity. So we have also here we have added to better understand this a positive feedback loop, because a positive feedback loop, it can generate this multiplicative growth that is needed to recreate these empirics. So that is basically that when the activity increases in some place, then that also increases the attraction in places close to that one. So if the city center grows, then the outskirts of the city becomes more attractive because you have access to more activities, more choices in the city center. And this kind of positive feedback loop is one way that can create those uneven distributions, that can explain that just 2% of the built area holds 50% of total land value. So, but then, as I said, we miss something else that can create this accessibility, which can explain why it's those specific places that holds so much of the land value. Because this positive feedback loop can explain the distribution, why it's just a few percent, but we need to explain why it's just these special places. So we miss something here. So down here you can see this last slide, but just presented in another way. I had to rearrange it. And as the heading is revealing, we have this missing link, which is infrastructure. The roads, the rails, paths, cycle paths, etc. Those ones are the one that creating this accessibility that makes it easier and quicker to reach different destinations. And that accessibility generates an accessibility to activities, an attraction in the place, and that generates more activity, trade, dwelling, etc. So there you have the positive feedback loop, and that generates the urban growth, that our cities grow and that the land value increases. So, next step, the urban growth will generate a demand for new infrastructure, for new roads, of course, because we will get capacity problems. And a lot of people want to commute to city center to work, we will get congestion on the roads, for example. And the railways as well can get congested. So we have some kind of demand here, some kind of which becomes, as we call it, organic growth, maybe reactive growth. And that is small projects, just capacity increases. Small roads that makes the city grow piece by piece, so to say. And that's why we call it organic, because it's just adding small short roads and the city is growing. But this generates a problem in the long run, and that is because small municipalities and single industries and residents, they don't have money to pay for large road investments. They don't have the willingness to pay for new highways and new train lines, because that is costing a lot of money. But that is a solution to this problem with congestion, this capacity problem. So we have another infrastructure driver, and that is the national road planning. And that is political decisions on national scales, and we call that infrastructure growth for strategic. And that is, for example, Statens vegvesen, and of course the Swedish Public Road Administration. And this is large roads and new long train lines that are costing billions. Because, as I said, a small city or just a group of industries, they don't have the money to do these large investments. So this strategic planning, these large, huge roads, they are changing the infrastructure in a very, very great way. Because a new highway, it will shorten the time to reach to other cities. We have seen this in earlier research in this Samfund group, that when you create new links, new fixed links, you're also creating new accessibility, and that is developing these areas that the demands will increase and the land values will increase. So what we need to understand is how these strategic roads affects the urban growth. And that is, as I said, it's many steps that we have to understand and that we have to model. And that makes it a bit complicated. So, our model attempt. As I said, this is a complicated way to take all those steps into consideration, but it's necessary to be able to understand how the infrastructure changes the urban areas. So, our model attempt, as you can see here, this is modeled land values. This is a very large-scale model that we're trying to build. And why? Because roads and settlements doesn't care about borders, about national borders. Basically, well, in Europe, because it's not any problem for me to move to Norway, to work in Norway. And it's not any problem for Norwegians to move to Sweden and work here. So this urban growth and the infrastructure projects, they are affecting several countries. So we need a model that can do this in a very large scale. And also to understand these large-scale infrastructure projects, how they affect the urban development, because the E39 is a very huge infrastructure project. I mean, if you look at this picture, it will stretch along a long coastline. So, but we also need to understand the implication of this large-scale infrastructure on smaller areas. We have small villages or small towns along these roads. So we need to understand how they are affected, because they are not only affected by the roads just around them, they are also affected by roads affected by larger infrastructure projects are affecting, for example, if you live in a small village but you can suddenly reach a larger town in 1 hour, then that will increase the land value, that will affect this small village. So we need to take into consideration these large-scale infrastructure and then be able to zoom in on smaller areas. So if we look at different types of models to do this modeling and to understand this urban growth, we can place the models into this kind of diagram where we have a number of parameters on the x-axis, and we have the predictive power on the y-axis. So first we have these urban economics models, as Fontynen, for example. They don't have so many parameters. Fontynen have basically distance to city center. That's just one parameter. But the predictive power, as I said, that is not so good, because you have to point out city center and there is just fixed distances. So people have tried to solve this by developing LUTI models. And LUTI models, they have a better predictive power, but also that is resulting from that you add more parameters. You have to have more input data, more parameters to tune, but then you get a better predictive power. But what we would like to achieve is a more simplistic model that doesn't require so many parameters, but has a good predictive power. And the number of parameters, if you look at a national model, or if you look at a more small-scale model, that might not be any problem. You can get the data easily and it doesn't cost so much. But if you want to do model over a whole country, or as we would like to do model several countries, then suddenly it becomes problematic to gather all this data. And this data can be different between different countries. So that makes it a problem. So therefore, we would like to have few parameters. And as I said in the previous slide, just go back here. We have just the infrastructure as an input parameter, or we have local conditions as well, but those are very small. So we would like to explain the urban growth basically by infrastructure as an input. So, this is, I mean, it looks very good to have a few number of parameters and have a high predictive power. But of course, it's not so very easy to achieve it. So, but that is what makes the research fun, that we're trying to find something that not so many has found before us, and try to make a model that can be used in this large scale so that we can assess the effects of E39 or some other very large infrastructure project. So the current state of our model. Here are the model predictions, as I said earlier. And here we can look at one empirical result. This is nightlight data, and that is the satellites take photos of the Earth at night. And then you can see all the light that we are generating by houses, by cars, etc. That is captured by the satellites. And this is quite good indicator of urban activity. As you can see, the larger cities and the larger urban areas are more lit, while the northern part of Norway and Sweden, it isn't much of activity there. And you can see this in the nightlight data. So those pictures, they are, we would say, quite similar and not exact. You can see differences, of course. But the model predicts around 60% of the empirical variations. And is 60% good or bad? This is 0.6 as R-square value in regression models. Well, it depends, I would say. In some research areas, 60% isn't anything. People are aiming at explaining 90%, for example. And in some research areas, just explaining 10 or 20% is a really huge achievement. In medical sciences, for example, they are very complicated models, and if you can just explain a few percent of variations, then you can be really happy. But we have said as a rule of thumb, if you can explain more than 50% of the empirical variations, of the land value variations, or the nightlight data, or population density, we consider it quite good model. It is useful. It doesn't capture everything, but almost 2/3 of the variations. So of course we are aiming at reaching higher values. We want to explain more of the empirical variation, and hopefully we will achieve that in the future. But we are quite happy with 60% because we have so few parameters, basically the infrastructure and just the local conditions is just buildable land. So of course you can take this model, you can add more parameters, and then you can explain more of the empirical variations of the empirical result. But that adding more parameters makes it more complicated. It takes longer time to run. And it's also problematic to get consistent data over country borders. So we are trying to develop this simplistic model, but if anyone would like to take it and add more parameters, that's fine. That might be an interesting project in itself. So now a little bit about the outcome of the model, how to interpret these results. And here we're taking this picture, as some of you might have seen. It was Teknologidagarna last year. We published this the first time. And this is where we have put in all the E39 projects, and we have run our model. And the results, as you can see, they're stretching from -10 to +100% in urban growth. This is assuming that we have no growth, no BNP, GNP growth. and that the cities are not growing at all. And that is unrealistic, I would say. And this is also assuming that the E39 is the only project, the only infrastructure project. And that is not true, of course. There are a lot of other projects that you have to take into consideration. But we got this question about the Oslo area that gets not a growth, but a decline of 10%. And what will that mean? Is it true? But I would say it's unrealistic to assume that nothing is growing and no other projects are made. So this map is just showing in this way a reallocation of the activity, the land value, or dwellings, houses, urban areas, etc. So, assuming 10% growth over the time that for the build time of E39 might be a more realistic value. And then we can see that these blue areas around Oslo, that means that we just have 0% growth. It's not growing. The economic development in Norway will be focused on the west coast. But as I said, this is just assuming the E39. You have to take other projects into consideration to be able to do a more realistic model. But we can also look at 20% growth, which might be a more realistic number because of the long time to build E39. And then you can see that Oslo area is growing. It's growing 10%. And the west coast is, of course, growing even more, like 120%. So, but what you can see in this picture is that if you just invest in the E39, you will shift the economic development to the west coast of Norway. So that is a very strong regional development effort, I would say. This will increase the urban growth and the urban activity, the economic growth on the west coast. But we have to put in other infrastructure projects to get a more realistic picture. But I would like to stress that just running our model, it shows just a reallocation. So you have to take the growth into consideration, and then you can see that Oslo is growing, but not as fast as the west coast. So that's a better interpretation of this model. So a little bit about the next steps in our project. We are going to make time series analysis in order to make the theory stronger. Because these studies, as you can see this picture, it's just a cross-sectional study. This is just looking at the reallocation. But we would like to look at changes over time to see if an infrastructure change really changes the urban growth. Because these temporal studies, retrospective studies in this case, they have a much stronger value as science than just cross-sectional analysis. Might be a little bit too much to call it that you can prove the theory, but at least you can make it a lot more plausible or probable by doing this time series analysis. And we will do case studies, both in Norway and Sweden, as I'm working together with Alexander, who is funded by Swedish Road Administration. And these case studies will be kind of similar to the research about fixed links. We will look at larger infrastructure projects that has built in quite short time. And bridges is a very good example of a very good case for this kind of study, because it suddenly shortens the time to travel between two locations dramatically. So there will be a lot of studies on this ferry replacement. Also because the E39 is very focused on replacing ferries. And the E39 will reshape the infrastructure in a very remarkable way. So, and we will investigate different empirical sources for validation. We have used land value so far, but we will look at population density and nightlight data. Nightlight data doesn't tell so much about what kind of result you will get. It's not very usable for predictions, but it's a very good, we have access to a very long time scale, so it's very good to validate the theory. But then land value might be, it is really good to be able to predict, because land value has it's a very huge influence on the urban development, because a high land value usually makes people to invest in larger buildings. So land value is really reshaping the urban area. And also population density. That is also a very good indicator and something that can be useful for the future. If you can run this model and you can see that this will make an increase in population density, that can be quite useful to meet these future demands in our planning. So we will investigate these different sources during this autumn. And we will invite you to a workshop with different stakeholders in the national road plan process to see what can each stakeholder get from this kind of research, how can they benefit from it, and how can they use the outcome. So what we would like to do as well, model or a tool where you easily can draw new infrastructure projects and see what the results will be, for example, for population density or building density or land values. Ultimately, we would like to have some kind of web tool where you just can make the suggested changes in infrastructure and you will get the results directly. Because that would make it very easy to compare different placements for the roads. What will happen if we move the road a few kilometers to east-west? What will happen if we don't replace this ferry or we replace another ferry? That would be very useful, we think, for future planning. So that is our ultimate goal, I would say. Right now, it's our model takes some time to run. So we have to work on that, and we also have to work on user-friendly interface so that anyone in the planning process, either on the national scale or municipalities can test different infrastructure changes and see what the consequences are. So we have a lot of interesting questions that we will deal with in the future. And we'll have a workshop where we'll discuss these results and also, of course, discuss future steps. So, having said that, I would like to thank you for having this time to present. I think it's really fun to share our ideas because we get questions and feedback that makes us think even more. As I said in the beginning, we have got a lot of questions that has questioned something that we has taken for granted. So we have to rethink and try to explain our reasoning and our background and our hypothesis. So thank you very much. Questions, thoughts?
Thank you, Leonard, for a very nice presentation. Your research is really interesting, and I'm looking forward to the easy draw model when it's done. That will be really nice tool to use. Yeah. So if anybody has question, you can ask your questions in writing in the message field, or you can just speak them out. So go ahead.
I have a question, Katrina.
Yes.
Looking at your model, Leonard, if you go back to the slide on growth. So that is a growth in population, right?
We are talking about, it can be both population or it can be...
Or is it an accessibility increase?
No, it's the result of the accessibility increase. So now we're looking at land value. So it's
this is land value growth?
Yeah, it's a land value growth or a GMP growth. Those ones are following each other. So it's not necessarily population growth, but this accessibility increase will generate more possibility, more attraction. So this is also an urbanization process in many ways, that this growth will make it more attractive to live in these cities, these towns along E39. So it might be a regional reallocation as well.
Yeah, okay. So how do you use like total number of people in Norway and distribute it again, adjusted for the changes in accessibility? Is that how you get these percentages, or?
The percentages are just from our model, but we can put in, let's say we just put in the population density in Norway right now, and then we run the model, and then we will get the result in the first column that we have no growth. And then we can see that, well, basically this is saying that people will move from Oslo to the West Coast, because the West Coast economy and workplaces that will increase, so it will attract people. But then we can put in these growth either in land value or population, and we can see that it is not the redistribution, it's not a reallocation, it's where the growth will take place. So it's possible to, now we're trying to do this very simplistic model, but it's possible to put in either economic value or population.
Yeah, okay. I was just thinking because people like to move often relatively short distances. So for many people to move from Oslo to the Western Coast, for instance, could at least take some time.
Oh yes. The model is you have a lag, of course, after the model, for sure. But this, and it might be a huge step to move from Oslo to the West Coast. But for the best paid jobs, the jobs that create that needs a longer education, advanced jobs, then people are moving long distances. The less qualified job people are not willing to move so long distances.
That kind of leads me to the next question. Have you looked into the literature on agglomeration economics?
Yes. That is one basis for let's say the justification for this theory. As I said, this 2% of the built area contains 50% of the land value. That is an agglomeration effect that we're trying to model. But we're trying to do this spatial model. So we would like to find out why these 2% are located where they are located. But it is an agglomeration effect, of course, because it makes it easier for people to work and trade and the interaction. So yes, it's an agglomeration effect, of course.
And that might explain why certain areas are more attractive than other ones, because they have a more diverse labor market and stuff like that. I don't know, do your model take that into account?
Exactly. That is what we are. More diverse labor market. Yes, it's a result of concentration of people. That the population increases and you can reach more workplaces. So that creates a more diverse labor market. So yes, that is, we're trying to model the spatial side of the agglomeration, so to say. A lot of people are trying to, so to say, look at the agglomeration of the whole country and see what happens when the cities grow and look at the total growth. But we are more interested to look at the spatial effects. Where does this agglomeration take place? But you're totally right that this is about agglomeration, but the spatial distribution of it.
It's very interesting to see these kinds of models at this kind of large scale. It's interesting.
Yeah, we are maybe aiming too high. I don't know, but we are really interested in looking at this large scale, because the E39 is a large project, so we have to take into account several nations.
Could I ask a question, Leonard? This is Kirsty here. Hi. I was wondering, because you have 3 columns on the left side with different, when the red is like 50% and the third one is 70%. So which one is it in the figure? Is it, or the map?
These numbers are just, how to say, this is a continuous map.
Okay.
So the colors are continuous, and then we just put some bars on certain places, so to say. But it's entirely continuous. You can look at any place and you can get very high precision percentage value. Of course, that precision is not entirely true. It's a little bit false precision. But what's interesting is that you can see this continuous scale, that you can see that the city center is very attractive, and then it's just a smooth decline. We don't, as I said, the problem with Fontinen's model is that we have very distinct areas. But he has a border that here does the industrial area and then here does the residential area start. But the reality is more smooth. it's more mixed up, and that is what we want to achieve with this model. So those percentages are just examples on the scale to see, get an easy understanding of.
Yeah. Could I just also ask, because I was a little bit puzzled by that, for instance, Trondheim and Kristiansand at the top and the bottom. Have you not done calculations there, or is there no growth and no effect of the E39?
We have not taken into consideration the sea link from Kristiansand to Denmark yet. We don't have any good model for ferries yet. We would like to implement that, of course. But the growth, because the road is starting in Trondheim and ending in Kristiansand, that means that people on the end points, they will not benefit as much of the road as people in the middle. Because if you're located in the middle, you can easily travel in both directions. But if you live in Trondheim, you will just get the benefit of traveling in one direction. So that is
that's true, of course. But in this calculations, have you considered mixing with all the other projects that are ongoing, or is it just the E39 and the effect of the E39 you have looked at?
We're trying to develop a general model, but then we're going to test it on case studies. Because it's, well, you can do some testing on the whole country, but we would like to do this case studies because it's, to build a new bridge is such a huge change. So you can see it's very easily to measure before and after. And just to look at the smaller infrastructure and capacity increases and looking at the whole country, it's not as easy to see the effects. But this is applicable to all infrastructure projects, of course. And the model itself, it has no limits to extend to railways and ferries. The only problem is how to weight those, to compare those. How attractive is it to go on a ferry compared to a bridge, or how attractive is it to commute by train versus car? So to extend it to more different transport modes, it requires some more thinking and some more research on that. And I know that there is ongoing research, so we would like to put that in, but the model is open for that, of course. So this is, and Alexander will do case studies in Sweden, while I do the Norwegian case studies. Yeah. So we will look at it large scale, of course, but then focus on these cases to see the strong differences.
But in your model, Leonard, is it just accessibility which is used?
Well, we have used this local premises, as I said. Let's see. Where we have it. Local conditions. But those are not very important. Those are basically a starting point. Let's say you have a very flat land, then it's possible to use all of that land. It's quite cheap to build. If it's a lot of mountains or clay, then you have to, it's harder and more expensive to build that land. And then proximity to water seems to, that's very, it's hard to model because it's a preference among people to live close to water. It's not any, well, it's kind of exogenous parameter. We have estimated it. We have quite good estimations on how much more people are willing to pay to live close to water. So we're putting that into our model, but it doesn't. I mean, the most important one is the infrastructure. That is really important, and the local conditions just change that a little bit. So it's mainly infrastructure.
So infrastructure, so that you have this accessibility measure, which mainly consists of the links between the different areas. Do you have a number of people or employees in that accessibility measure? Or?
No, we're just looking at
density.
infrastructure, what the infrastructure makes it possible to reach, so to say.
Okay, so the travel time between different places.
Yes, exactly. Mm-hmm. Because we are trying to model the reality, so to say. So our model is, you can see it as a parallel track. We have the reality, and there are certain developments happen, but we are trying to make a theoretical model of that so that we can predict the future. So that we can run our model and see what will happen in the future to a certain extent, as I said, 60% right now.
And the attraction part, which is on the left side there, that is, what is the attraction? Is it?
The attraction is basically how that we say that a place, the attractiveness of a place, is dependent on how much activity you can reach, how much other attractive places you can reach. If you are, for example, location in a city center, then you can reach a lot of places, of course, but you can reach a lot of places that also have a good location. If you're situated more in rural areas, you can reach a lot of places, but there is nothing happening in those places. So we're trying to model that feedback loop, that when one place becomes more attractive, then other places around it becomes more attractive as well. So this is increasing. And that you can also see that in general urban development, that when a city becomes larger, it becomes a more diverse labor market, people earn more, and the city becomes more attractive. So more people move to it. And when more people move to it, it grows even larger, it becomes even more attractive, and so on. So it's feeding itself, so to say. And that is what we're trying to model, and that's a little bit tricky. It's a bit unstable model.
It might help you to have the data on number of employees or population within different zones. I don't know, but you maybe don't have that data.
We have it, but the problem is that it's a bit different between different countries. You're counting in different ways and different time series and so on. So, of course, the model will be better if we add it, but we would like to wait with that. We would like to try to develop this model as far as we can, and then we can add more parameters. Because, as I said, the more parameters makes it more complex and more demanding, and some data is really expensive to buy, and that makes, if we're going to make a tool that's easy to use, we would like it also to not demand any data that costs a lot, because we would like it to be used among as many people as possible, as many planners as possible. So right now we're using the OpenStreetMap, which is a totally free community-driven database of all the roads and ferries and trains all over the world. There is some mapping companies that donate to the basis for this OpenStreetMap, but now it's community-driven, and it's pretty good. We have compared it to other sources, and it works very well. So we would like to keep this model small and cheap and simple to start with, and then you can add other parameters to it.
And the validation of the model, what did you compare? How did you find out that 60% was?
the 60% is, that is, as I said, around, it depends a little bit on different regions and so on, and which time. So for some areas it's more like 50%, and for some areas we can predict 80%. And it also varies based on how our input parameters are changed. For example, how much time are people willing to commute? I mean,
and you're predicting population density.
Right now we're predicting land value.
Land value, okay.
Yes, and we will go into population density, and those ones, they are correlating quite well. If there is a lot of people living in a small area, then the prices go up for all kind of developments. You can see that in central part of our capitals, its prices are almost ridiculous. While in the countryside, you can get very nice houses for nothing. So the population density and the land value and also the nightlight data, they are correlating quite well. So we're looking at each of them to see what does the model tell, and as I said, the data availability, land value is available quite good, but just for the last 20 years or so. But the nightlight data is available for 30 years almost. And the population density, well, that's not as regular intervals. That's kind of they're calibrated each 10 years or so. So these different empirical sources, they are they're different in availability and cost and usefulness. So we are trying to explore them all, you see. We are also thinking about building density as a parameter, but that data is harder to manage. It's a very much data to get.
Okay, I think we are running out of time. So I'm sorry to interrupt your very interesting discussion here, but I think the two of you should definitely talk more.
Oh, yeah.
And by that, I think we will say thank you, Leonard, and I will now stop the recording.
Yep, thank you as well.